Let's do the second part of the problem. Again, we are given another vector field in R3, and first we need to show that this vector field is conservative. So I did that work and it showed that our vector field F is conservative, and I expect you to go over this work to show that a three-dimensional vector field is conservative. You just need to, what you need to do is you need to calculate the curl of this vector field, which is given here, and if this curl of this vector field equals to the zero vector, then your vector field is conservative. Great. Since this one is conservative, now we know that we have a scalar function little f, so that its gradient equals to the given vector field. Now, so again, our goal is to figure out what this little f is. So let's consider the gradient of f, which is partial f of partial x, partial f of partial y, and partial f of partial c. That's the gradient of little f, and this equals to the given vector field f, and the vector field f is this. Okay, now we can construct the equations. So if we compare the first component, we have partial f of partial x equals to y. Let's say this is our equation 1. Partial f of partial y equals to, I will write x first, x plus c times cosine of yc. It's the second equation, and finally we have an expression for partial f of partial c, and it equals to y times cosine of yc. Great. Okay, now again, let's consider equation 1. One, we have partial f of partial x equals to y. Okay, now to find f, we have to integrate both sides with respect to the x variable. Okay, and if you do that, you will get f of x comma y comma c. In general, this little f can be a function of x, y, and c. So my little f equals to integral of y dx. If you integrate y with respect to the x variable, you will get the constant, which is y times x, plus now we can have a function g, and g can be a function of y and c only. Okay, great. So at the moment, we know that my little f should be in this form, y times x plus some function that contains only the y and c variables. Okay, so now let's differentiate this one. Let's differentiate this one with respect to the y variable. So partial f of partial y equals to, if you differentiate this one with respect to the y variable, you should get x plus partial g over partial y. Okay, let's say this is our equation number 4, and equation 2 says partial f of partial y equals to this. So okay, this is my equation 2, So if we compare equation, let's compare equations 2 and 4, because both the equations represents partial f of partial y. So it should be x plus c cosine of yc equals to x plus partial g over partial y. Now if you simplify this equation, so you can cancel this x. Now you have partial g over partial y equals to c times cosine of yc. So our next target is to figure out what this g is, or what this g should be. So let's, okay, I will write partial g over partial y in the left hand side. Okay, now since this involves derivative of y, to get g we have to integrate both sides with respect to the y variable. So then g of y comma c equals to integral of c times cosine of yc dy. With respect to the y variable, we have to treat c variable as if it is a constant, and if you integrate this you should get c times integral of cosine is sine of yc, but now so we have this constant c. If you integrate cosine of y times a constant, you should get sine of y times the constant over c, that constant, plus now we should add a function of c. Again, the reason that we add a function that contains only the c variable is if we differentiate this equation with respect to the y variable, you will get c cosine y of c, and derivative of h of c with respect to the y variable is 0, because this one contains only the variable c. Okay, now let's simplify this. We can update our g of y comma c equals to sine of yc plus h of c. Okay, now let's go ahead and update our function f. So initially we have our little f equals to x times y plus g of y comma c, but here we found that g of y comma c equals to sine of yc plus h of c. Now my little f should be xy plus sine of yc plus h of c. Great. Okay, so far we have used the derivative of f with respect to the x variable and the derivative of f with respect to the y variable. So our next goal is to compare the derivative of f with respect to the c variable. So let's calculate partial f of partial c. So this is 0, and you should get cosine of yc. Now we differentiate with respect to the c variable, therefore we have to treat y as a constant. So we should get times y plus derivative of h with respect to the c variable. Let's say this is our equation number 5. So now at this point we have to compare. Let's compare equations 3 and 5. is 3. 3 is this. So we have y of cosine yc equals to cosine of yc times y, which is the term in the left hand side, plus dh over dc. Now we can cancel this with that. Finally, we have derivative of h with respect to the c variable equals to 0. So now let's integrate both sides with respect to the z variable. Okay, and the right hand side is h of c. Now integral of 0 is 0. Now we need to add the constant of integration, so let's add c. So this means our function h should be a constant function. Okay, now we can update this equation. So my f should be xy plus sine of yc plus some constant. Okay, so this is the way we calculate the scalar potential function for a conservative vector field in R3.